Here we're going to look at a function where not only is it like possible to rearrange, but in fact it's going to be necessary. And this is when the method of rearranging the order of integration is the most powerful and most useful, because it allows you to take an integral that you otherwise would not be able to evaluate and turn it into something that does have an answer. So we're going to evaluate this integral. And first of all, we should look at why the inner integral as written right now is not evaluable. Why can we not get a value for this? Well, if e to the x to the fourth were e to the x to the fourth times something like x to the third, then we could look at this as the u and this as the du, and then we would have something to cancel. But e to the x to the something, some power, that all by itself, without that du factor on the outside, you actually can't get an integral of that. So it's not even just that this is hard, it's that it's impossible. So there's only one way to do this, and it will be by rearranging the order of integration. Just a note, this doesn't make all problems doable. You will still have the occasional impossible integral that you'll just need to like numerically approximate, for example. But this is meant to give you a hint of like, if you can't evaluate an integral, one of the options is to reverse the order of integration. And sometimes, not always, but sometimes that does turn something from impossible into at least possible, if not easy. Just like with the prior problem and with most double integrals, you should sketch the domain of integration first. So this says that x goes between cube root of y and 2, and y goes between 0 and 8. All right, let's get a picture of that. That's going to look like this. X equals cube root of 8. We would much more commonly write this as y equals x to the third power. So that's going to be this function. Y is going to climb up and then go up like that. X is going to go between that and 2. It will be greater than this and less than 2. If it's less than 2, that means it's to the right of 2. So this is going to be x equals 2. And we're looking for stuff that is in between these two. So that would be like this portion right here. Y goes between 0 and 8. These are custom made for each other because y reaches 8 at the same time that x equals 2. So a way of reforming this domain of integration by reversing things would go like this. Y would go from 0 up until x to the third. So you don't want to just write it as a rectangle. You don't want to say that y goes from 0 to 8 and x goes from 0 to 2, because that's bad. That misses the complexity of this. But once we've said that y goes between 0 and x to the third, now we have flattened the domain down to just an interval of x values. And x now will go between 0 and, can you guess it? Yes, it's going to be 2. Notice how the 8 is programmed in the same way that the 2 was programmed in before. So even though 8 never gets mentioned, this is the same domain of integration. So this is going to be equal to the integral along along x on the outside of from 0 to 2, and then integral, that's a bad integral sign, integral along the y from 0 to x cubed. And same function, e to the x to the fourth. Now we're doing y first and then x. Notice how when I pointed out at first why this problem was impossible, it was because it was missing an x to the third term. Looky, looky. So now we're going to have something really convenient here. Let's make it happen. This is going to be on the inner integral from 0 to x to the third of e to the x to the fourth dy. Well, e to the x to the fourth is a complicated thing from x's perspective, but from y's perspective, it is a constant. So this will be y times e to the x to the fourth. As in, like the integral of 2 would be 2y. So this is integral of e to the x to the fourth is y times the constant. This will be evaluated at y equals 0 and y equals x to the third. This is x to the third times e to the x to the fourth. The 0 version has a value of 0. So this is the result of the inner integral. The outer integral is going to be integral from, what was it, 0 to 2 of x to the third times e to the x to the fourth. And look, like magic, we have that integral that we wanted for the x because now the du is there. Let's do it by substitution. U can be x to the fourth, meaning that du is going to be 4x to the third dx. Isolating dx, we get that dx equals du over 4x to the third. Moreover, u of 0 is 0, and u of 2, if you raise 2 to the fourth power, that's 16. So this will become integral from 0 to 16 of x to the third times e to the u times, and now dx has become du over 4x to the third. Of course, the payoff here is that x to the third goes away. The 4 does need to stick around. So that's going to become integral, well, I'll say 1/4. I'll take it out to the front. 1/4 integral from 0 to 16 of e to the u du. We already know the integral of e to the u is e to the u. So this is going to be 1/4 e to the u evaluated at 0 and 16. And this is, well, it's elementary now. It's e to the 16th minus e to the 0, both over 4. E to the 0 is 1. So e to the 16th minus 1 over 4. And there you have it.